קודם כל, תודה שבאתם. חלקכם מכירים אותי, מי שלא, אני עדי נורקין ממחלקת ההשנאה של אנג'יס. אנג'יס בשותפות עם דובל כבר 16 שנים, וב10 שנים האחרונות אנחנו מיישמים את שירות ה-EMI בהצלחה גדולה אצל הרבה מהלקוחות שלנו. אני רוצה להגיד לכם שיצא לי לעבוד על המצגת עם ג'יימס, והולך להיות וובינר מאוד מעניין, עם דגש מיוחד על הפרקטיות והייחודיות של הבדיקות EMI וה-ESMA. אורך המצגת יהיה כשעה, עם עוד 30 דקות בסוף המצגת לשאלות, אבל ג'יימס ביקש שתרגישו חופשי לשאול שאלות גם תוך כדי. יש את הלשונית questions אצלכם, את השאלות אתם מוזמנים לכתוב ולהגיש בעברית או באנגלית. עדיף באנגלית, ככה התשובה של ג'יימס תהיה יותר מהירה ומדויקת, אבל גם עברית זה בסדר ואנחנו נציג לו את השאלות. אני עכשיו אציג לכם את ג'יימס, אנחנו נעבור בעצם לאנגלית, ומיד אחרי זה נתחיל. So allow me to introduce James E. Timperley. James began his career with American Electric Power. He was involved in station engineering, establishing an electrical R&D laboratory, and developing a large motor repair shop, as well as implementing procedures for inspecting, repairing, operating, upgrading, and maintaining motors, generators, and isolated phase bus systems. While with AEP, he pioneered the EMSA, electromagnetic signature analysis. He retired from AEP after 38 years and joined Doble Engineering. In Doble, his activities included training new engineers, the application of the EMSA, testing and maintaining high current isolated phase bus systems, and equipment root cause failure analysis. He retired from Doble in 2019 and has established the J.E. Timperley Consulting to continue services to the industry. James has published over dozens of technical paper and delivered scores of conference presentation over the past 50 years. Mr. Timperley is an IEE Life Fellow and was presented the 2006 Dakin Award by the IEE, the Electric and Isolation Society for Development of the EMI Diagnostics. He was registered engineer in Ohio for the last 40 years. And without further ado, let me introduce you to James. James, the stage is yours.
Okay, well, thank you very much. If you'll switch the control over to me, I'll bring up the PowerPoint.
Of course.
Okay, very good. To show my screen, and let's see if this works today. I hope you can see the presentation. Can you?
We can see it.
Very good. It works. Excellent. Whoops. Now I went back to the other one. Okay, let me get this down. We'll get it yet. My fault. There we go. As he mentioned, we're talking about the application of EMI, which is electromagnetic interference, and the analysis of that to optimize operation and maintenance planning at industrial sites. This equipment failures can be reduced and condition-based maintenance can be improved with the application of EMSA, electromagnetic signature analysis. The technique was pioneered by American Electric Power and has been applied at hundreds of power plants, petrochemical sites, and industrial sites since 1980. And this includes most of the combined cycle generator systems that are out there now, petrochemical sites, gas turbine sites, steam turbines, and LNG facilities. The condition of motors, generators, and transformers, bus, switchgear, can be determined from the first test. Trending is important, but not necessary to identify a problem. The return on investment to pay for doing the test versus run to failure on equipment is about 10 to 1 just for repair costs, not lost production. Here's testing a large compressor motor at a site, emergency standby generators, a refinery. We also test transformers, the bus, and on the high voltage side of the transformers out into the switch yard, we can find problems. And then the more common large generators, the isophase bus, and the breakers on the bus. High voltage discharges are usually considered a partial discharge. That and low voltage arcing, where there's current flow, produces light. You can see the discharge, the spark. Ultraviolet is also produced. There are chemical changes. Ozone will be produced in air, O3. Hydrogen is produced if the discharge is under oil. There's a sound produced. It can be an audible noise. You can hear the sizzling of corona. Ultrasound is produced. If it's really bad, like an arc, you'll produce heat, so infrared can detect it. And there's radio noise produced, EMI. And that's what we're going to be talking about, is the radio noise, or the EMI. The EMI signature and pattern generated by a defect is unique for the location of that defect and what type of defect is involved, and we'll discuss that at length. Maintenance recommendations and condition assessment can be made with the first test, like I mentioned. Trending is important, but not necessary to identify deterioration. Many test methods say they collect data, retest in 6 months, retest again in 6 months, and then they'll tell you what the problem is. With EMSA, we can determine what the condition is on the first test. What I like to stress is that we can determine when there is no problem. So if a particular generator or motor or transformer has no problem, then you can focus maintenance only when and where required on other pieces of equipment. Data is collected from the temporary installation of a split core radio frequency current transformer, RFCT. This is placed around a power conduit, a safety ground, or neutral. Here's the RFCT on the HO ground on a transformer. This goes up to the HO bushing. Grounding transformer on a small generator. This goes up to the neutral of the generator. And here's the safety ground on the side of a GE generator. No hot connections required to any energized conductor. There's no interference with operations, no arc flash hazard. Data collection takes roughly 1 hour to finish. EMSA is applied for motors. Here the probe is placed around the motor power conduit when it's available. Then you remove it. There's no safety problem, and there's no interfering with normal operations. For most motors with one power conduit, the RFCT is placed around that. If there are 2 conduits, we take the one on the right. If for some reason you can't get at the conduit, then we can put the RFCT on a safety ground to the frame of the motor. I've even used an oil line, a bearing drain line on large motors when neither one of those were available. The signature that's collected is unique for each location and motor design. Identical motors will have very similar signatures, and if they're at the same location, they can be directly compared. Problems identified with the first test. Trending will then verify maintenance was or was not successful, and we'll show examples of that later. The feed water motor here has no problems. Now this is called the EMI signature, and this is what we're analyzing. The vertical scale is microvolts quasi-peak. It's a logarithmic scale, so we can show very small and very large numbers. Quasi-peak is the special detector used in CISPR 16, which is the standard that EMI measurements follow. Quasi-peak was designed to pick up noise. Everybody's heard of an AM detector for radio or an FM detector for radio. Well, quasi-peak is like that, but it's designed to pick up noise. The horizontal scale is the frequency. So this is 10 kilohertz, 100 kilohertz, 1 megahertz, 10 megahertz. So it's an amplitude versus frequency plot. When you collect this data, you go back and look at the videos at various frequencies and you determine what this is. So in this case, where it was high here was random noise. This is a process carrier in that plant, and then also random noise and carriers here. This is almost the noise floor of the equipment, 0.1 microvolt. So you can see it's extremely sensitive. There's nothing wrong with this motor. It's in good shape. These two 4 kV motors are at a big coal-fired plant. It has a motor in the middle and then a pump on both ends of the motor. So there's 2 pumps and 1 motor. You have to have insulation on that shaft or you'll get circulating currents. Well, the number 2 motor is running properly. Here's a power line carrier off a transmission line system. More data carriers. Here's the AM radio down there. But motor number 1, they left the insulation out and they had sparking at the bearings. And that's the difference. So these two can be compared. Obviously, number 1 has a higher reading and a different pattern. I can't see the AM radio stations, so that one needs to be inspected. Induction motors often will develop broken rotor bars if it's a very high inertia load and there are many starts, such as a large fan. This one in Wyoming had been repaired in the past, but with the first test, we could see from this pattern that it developed cracked bars again. And here's a picture of a cracked rotor bar on a machine. This pattern is very unique. The arcing happens at a very low frequency of less than 1 hertz. It's the slip speed of the rotor. And how you verify that was this little device we call an EMI sniffer. We check the outboard bearing, we check the inboard bearing, we check on the other side of the coupling. So if you pick up here and here, and it's this arcing at a very low frequency, that's a broken rotor bar. Also with this, you can check if you got a coupling misalignment. If we had steady arcing and it was on the outboard bearing, the inboard bearing, and the other side of the coupling, then you have a misalignment and that coupling needs to be inspected. This old motor was at a plant down in Texas, 2300 volts. The H scale is the magnetic field scale on the sniffer, very insensitive, and this had so many broken rotor bars in it that we could measure it well over a meter from the motor, full scale with minimum gain. So continued operation was not recommended. You notice I said 2300 volts. EMSA is good for voltages 2300 volts and higher. Most partial discharge testing is good only for 6.9 kV and higher. At this site down in the Dominican Republic, they had 2 identical LNG pumps, cryogenic pumps. The alpha pump is the black. Here's the FM radio stations. There's no AM radio station seen. The Baker pump, the red line, has higher activity and very high activity out here at around 40 or 50 megahertz. It's very unusual to get very high frequencies out of 4 kV machines. So we asked them what the problem was, and they said they had trouble with a 4 kV bushing that they had repaired. Well, the repair was not successful. They needed to pull that B pump and replace that 4 kV bushing. Here's another comparison of 2 large air compressors at a plant. This Baker motor, here's a power line carrier, radio transmitter, AM radio stations, a peak here, which is dirt starting. Pretty well stops at about 30 megahertz. The other motor, the 1A motor, had very high readings right above 1 megahertz. And that's a typical signature for contamination on stator windings, is high corona readings near 1 megahertz. Also, we had some sparking, which was a different pattern, and with a sniffer, we could tell it was the outboard bearing. So this motor really needs to be removed from service, cleaned, and the bearing repaired. If there is a backup available, this is a small power plant up in northern part of California. We took data online and offline. The red curve is with the motor disconnected from the system. The black curve is with the motor fully loaded to 500 horsepower. And you can see the two are almost identical. So there's no difference between full load and zero load. All of the signature that we're seeing is the ambient noise at that site. And in fact, what we could pick up in this location is the 10 megahertz National Bureau of Standards time marker at 10 megahertz. So it's a very quiet motor. So there's nothing wrong with the motor, the power cables, the switch gear, the transformer, the bus feeding it. No maintenance is needed. The other motor, by the way, was exactly the same. One surprise with EMSA was we can pick up stator electrical problems, but we can also identify mechanical problems. Here's an EMSA signature for a water pump that had a problem, and that's the black line. Very high sparking going on. With a sniffer, we determined it was a bearing. They have 3 motors. They only need 2 for operation. So they took it out of service, repaired the motor bearing, put it back in service. Then we went back down the next month. This is what they saw. I would assume this very severe bearing wipe happened during shutdown. I can't believe it was running that bad. The bearing would have overheated. So they had a minor rub, and then that got much worse when they took that motor out of service. But anyway, they changed out the bearing. We went back. Here's the second set of data. All we're picking up is the local radio stations there in West Virginia. And so this pattern is gone. This one looks normal. There's nothing else. The motor system, again, the motor, the cables, the switchgear are all in good condition. No maintenance is needed. EMSA is applied for generators. This particular site has 5 gas turbine generators. What I'm showing here is CT1 and CT4. CT1 brushless exciter, the black curve is there. Very low readings with the brushless exciter on CT1. The brushless exciter on combustion turbine 4 is much higher, and it has arcing. And we'll go into this detail a little bit more later. But here, a direct comparison to these. The other machines look like CT1. CT4 was the only one that had a bad exciter. And we'll detail that later. We find a lot of open connections. This one, an open generator neutral ground, was found on several machines. An inspection found the connection at the neutral open. course, continued operation without this ground protection is not recommended. In one case, we found the disconnect switch going to the grounding transformer had not been closed after an outage. In another instance, a cable burned open from a recent transformer fault. The blue curve is the first connection. We put the RFCT around the conduit going up to the generator. Flat line at the noise floor of the receiving equipment. No signal. That cable is not connected to anything. It does act like an antenna from here up. So we get this pattern because there was some arcing of shaft currents at the grounding brush on the shaft. But this says it's open. So we move the probe to the ground of the generator, the safety ground, and we got the red curve. So that was the one we used for data analysis. And when they did the inspection, they found that the cable was opened up here. All of these connections in the grounding cage were good. Here's a safety ground open on a GE generator. This particular site has 4 identical machines. Unit 1, Unit 2, Unit 4. The signatures are almost identical. Really nothing wrong with those generators, but the safety ground on 3 is open. And we find 1 or 2 open safety grounds every year. We've seen it on motors, generators, transformers, and isolated phase bus. Particularly very old plants, that safety ground can open up from corrosion. Also in some brand new plants, and in fact that was the case here, these generators are only about 5 years old, and this 4-aught cable went into the ground, but it didn't connect to anything. So that was bad construction. Many types of electrical generators have been tested. Hydro generators, internal combustion engine driven generators, steam turbines, combustion turbines, nuclear turbines. A lot of generators have been tested. We'll get into it later, but we found over 20 conditions and problems that have been documented. Most of these can be identified on the first test. Data trending is good. It's particularly good to verify that no problems are developing or that a problem is developing. At this petrochemical site down in Louisiana, gas turbine 500, here's data from 2012 in green, 2013 in red, 2014 in blue. Really nothing going on. We like radio stations. They make very good benchmarks. So when you see very strong radio stations versus what's coming out of the rest of the system, it tells you that verifies there's no problem with that generator or transformer. So it's very good. It's interesting that year by year, some of these other data signals disappear. This one, for example, was there in 2013. And it was gone the other years. Here's another group of transmitters that come and go, and that's not at all unusual. Here in 2012, this radio station was very high, and then it kind of disappeared. At that site, they have, like I said, several similar generators. We've been testing there for almost 20 years now. Gas turbine 800 is developing problems, and an inspection should be scheduled. We also recommend that you wind winding supplies ahead of time, wedges, filler strips, and that sort of thing. Otherwise, an emergency order will be very expensive. And since they have 4 machines that are identical, they really should have winding supplies in stock anyway. So here's GT800. This is the 2017. See, the radio stations are very strong. Red is 19. This is the one that was just done this year. It continually goes up. This part here describes what's in the slots. This part here describes what's in the end windings. This part over here describes the isophase bus. So it looks like they have loose end windings and they have stator bars that are loose in the slots. So they need to schedule an inspection and probably make some winding repairs. Another thing that works quite well was pioneered by EDF in France with partial discharge testing on their big units. And that is compared data at 2 different loads. So we try to do it as much as we can, as high a load as they can get, and then about 70% of that. And this is 2013 data on this 143 MVA generator. 70 megawatts, we get this curve, the red one. At 100, we get higher readings. The windings are loose. They're vibrating more at 100 megawatts. So again, they need to schedule an outage, pull the rotor, and probably re-wedge, reblock, and tie the end windings. The other thing that verified that was the video pattern that we get. This was 1.7 megahertz, 1.5 megahertz. And what we're doing is we're looking at the pattern right here. What does that EMI pattern look like? And this is what we get. It was mostly corona, looks like a sine wave, a few partial discharge spikes, really no serious problem in 2012. The next year, we get some very tall partial discharge spikes, and this opening down here where it's a little bit wider, that's arcing. So that change in pattern at this area indicates also that they need to plan an inspection and do some repairs. When they got into it, they found this very, very minor partial discharge activity going on, and that's good. You want to catch it very early before serious problems develop. One of the nice things about EMSA is it is one of the very few online diagnostics for exciters. And all types of exciters have been tested. The old DC generators, like are still found on large hydro generators, brushless exciters, alternator exciters, and static exciters. A large brushless exciter shaft driven these days, there's a pilot generator, the main alternator, a diode wheel for changing this high frequency AC into DC, and then that connects to the rotor, the field of the main generator. Static exciters, the big ones, are fed directly from the isolated phase bus. They'll have a transformer cubicle, and then the rectifiers, and then the control unit. And all of this can be scanned with the sniffer, as well as all of this can be scanned with a sniffer. The pattern that we see, the video pattern, as I say, looks like a picket fence, a lot of spikes. And this is caused that when the diodes turn off and stop conducting, they usually chop current. So they oscillate a little bit and they produce a radio frequency. They produce EMI. It's a steady pattern. It does not change. The top of it may be include a sine wave like this one does. It may be straight across. That depends on the design of that exciter. So each one is unique, but they don't change. If one of the spikes is missing, that diode circuit is open. And almost all of these are a full wave rectifier. So they're 6 spikes and then they repeat again. Here, one circuit is open. A diode has shorted and a fuse has opened up. If there's a wide spot down at the bottom, that shows arcing. So here, all of the diode circuits are working, but I've got arcing present. So is it in the slip ring if it's an alternator type exciter, or is it a bad connection in the brushless exciter itself, or is that the slip rings? Here is one down in, I think this was in the Dominican Republic. We picked up this pattern here. So we knew we had arcing. We used the EMI sniffer, and this LF is the scale that we use, the range. 8 is the gain, 7 is the reading. So on the slip rings, we got a reading of 7. On the generator itself, we got a reading of 3. So the slip ring may be sparking. We went underneath the generator and the reading was now 9. Well, it only goes up to 10, so we had to cut the gain down from 8 to 6, and we got a reading of 5. So the reading got higher as we went down to the static exciter cubicle. It was not the slip rings that was sparking, it was in the static exciter. Here's that cubicle. Here are the cables going up to the slip rings. There's 2 conductors in each one of these cable trays. And they did an infrared scan and they found out that one of the cables was very warm. The other 3 were not. So they took an outage that weekend to find out what was happening. And when they opened up the exciter rectifier cubicle, they found one cable connections had overheated. It had not been torqued properly. So all the connections were cleaned, connections properly torqued, returned to service. They did an infrared scan, and now all 4 cables were the same temperature. So they had found the problem of one bad conductor and they corrected it. Here's another case. All of the diode circuits are good. We have this arcing. It's not at every spike. So that tells you it's a mechanical problem. And again, you could see the sparking on the slip rings in this case. So sometimes the sparking's at the slip ring, sometimes it's in the rectifier itself. This was a large engine-driven, internal combustion engine-driven brushless exciter. They had just come back from an outage. They had put in new diode modules, and we did the testing, and here's the arcing pattern. Now you see there's a lot more spikes. This particular one runs at a higher frequency than what this one does. This one is a static exciter that runs off the power frequency. This is an alternator that runs off a higher frequency. I've got arcing. So they took it down and they looked at it, and what the guy had done is he had over torqued one of the screws and stripped the threads and just left it. So they were happy to find that because eventually that wire would have come out. EMSA for transformers and switchgear. Most transformers are in very good condition. There's no PD or arcing inside the tank. Since they're connected to the grid, you have long transmission lines, so you pick up a lot of radio signals. And these are good benchmarks to whether there is or is no problem. This particular one was connected to the combustion turbine 2 at this site, 230 kV on the high side, 13.8 on the low side. Power line carriers for relaying and data transmission, radio stations, shortwave radio stations. This is down in the Caribbean. We pick up a lot of shortwave stations down in the Caribbean, and FM radio stations. I believe this is in Puerto Rico. They have AM radio stations. A lot of the other Caribbean islands don't have AM radio. So there's nothing wrong with that transformer. All these radio stations are much stronger than what we're picking up from the transformer. For dry type transformers, the #1 problem is contamination. The pattern is either corona or random noise. In this particular case, they had been sandblasting near the unit, but they did not mask off the ventilation. So what we had was process noise from that site, which is a lot of data transmitters. We had corona peaks, 2 of them. Again, one at 1 megahertz and one of them a little bit higher. and that's from contamination. So 6.6 kV, that can track. So what the recommendation was to take the transformer out of service when they could and clean it before they did get tracking. We did not see any tracking, just the contamination. This particular one is down in the Dominican Republic. We tested this transformer, broadband corona, severe partial discharge activity, very strong FM radio station. No AM radio could be seen. It's covered up by this noise. We used the sniffer and we scanned the tank and found no partial discharge activity at the transformer. So we walked the line down to the switch yard, which was almost a kilometer away. Very good distance between the transformer and the disconnect switches. And this is where all the arcing activity was going on. Gang operated disconnect switches on an SF6 breaker going to that transformer. It's near the Caribbean, a lot of salt water, a lot of rust. So they needed to clean those switches up. There was a problem with the switchgear. This is a petrochemical site down in Louisiana. We've been testing there for almost 20 years. It is a very complex bus system. They have several generators. They have several buses. They have series reactors to limit fault current so the breakers will work. It is getting 40 years old, so there's a lot of problems. In 2009, somebody had left a bag of bolts, plastic bag of bolts, inside the cabinet on top of the bus conductor. And that's what we got here on this P2-1 switchgear. We got all of this arcing, and it was a bag of bolts laying on the bus conductor. They opened it up, they found the bolts, they took them out, and of course in 2010 it was down to where it should be. Here again, here's the AM radio stations, and here's the FM radio stations. We were there again this year, and now some of these series reactors have loose connections. There's several of those reactors they need to inspect. So like I said, it's a complicated system, and they have a lot of problems. You can apply EMSA to power cables and either isolated phase bus or non-segregated bus. Power cables do not have mica insulation. They should have no PD going on, so there should be no radiated RF signal from them. So here we are testing at a transformer at a plant with many generators. Here's the cables going in, and you can use the sniffer and check each one of these cables. If there's one that has a problem, both in the terminations or in the cable itself, that will stand out so you can determine which one is bad. Wet cables can be identified, as I'm showing here. These are service water critical motors at a nuclear plant. The 1B motor, there's almost no noise at all. We stopped at 30 megahertz, below 10 megahertz on this one. Local radio station, this is the noise floor of the equipment. So the 1 Baker motor and cables are fine, but 1 Alpha is much higher. 1, 2, 3 orders of magnitude more noise. It was corona. And they opened up that tunnel that this cable was in, and it was full of water. So that was the signature of a wet cable. So comparing two at the same location, obviously 1A you need to work on. Here's a 138 kV cable where they tie from the power plant into the grid. So this is quite some distance from the plant. And again, the transmission lines make excellent antennas. Power line carriers from the grid, AM radio stations, FM radio stations. Unlike partial discharge analysis, EMSA identifies all of these signals. And like I mentioned several times, they make good benchmarks. Alpha and Bravo phases are basically the same. The Charlie phase is higher. And using the sniffer, we also verified that the Charlie phase was higher. So, okay, what do you do now? Well, you can do an infrared scan, or you can do an ultrasonic scan, or maybe use a coronoscope to see what the problem is where those cables attach to the transmission system. There'll be a pothead up there. There may be a potential transformer. There may be a surge arrestor. There may be a disconnect switch. So there's a lot of connections where these cables go into the grid. So we've picked up a problem. Now you need to apply some other tests to verify what that problem is. Isolated phase bus and non-segregated bus are easily tested. We've been doing this for a very long time. We found several problems. There is a lot of safety grounds involved in the system. So what we do, here's an I-beam that supports the bus, which is up here, and that safety ground goes to the ground mat. We put the current probe around one of those safety grounds. So on GT4, this is what we got. Very strong radio signals and a lot of discharges here on the higher frequencies. This is where isolated phase bus noise shows up, is right around the FM radio stations. It's not too bad because it's not much stronger than the FM radio or the AM radio, but there are some discharges in the bus. Almost every bus will have some discharges all of the time. I think in 40 years of doing this, we've only found 3 or 4 buses that had no PD at all. Almost every bus has some minor PD like this has, and it's not a problem. The most common problem with transformers is loose bolting after you do a Doble test on the transformer. At this particular site in Wyoming, the contractor had no written bolt torque procedures to follow. The sniffer traced the strong arcing that we saw here, again around 1 megahertz, to the connections for the non-seg bus going into the side of the transformer. This is where the arcing was taking place. And when we told them that, they said, well, we've had failures there before. Well, this basically is because there was no written procedure by the contractor to follow. This is at a nickel smelter in the Dominican Republic. Again, this is the amplitude. This is the frequency. It's a fairly small generator. They ran off of a chemical compound that they produced with a little refinery there. And here's the bus discharges. Not that strong, but definitely something going on. When we looked at the pattern at 26 megahertz, which is the spike right here, here's what the pattern looks like. Notice the top of the discharges are not the same. I've got 3 discharges per positive and negative half cycle. The tops are not uniform. That tells me something is loose. Something is moving. So we recommended an inspection for the bus, and they were able to come down, I think 2 weeks later, and look at it. Usually the problem with the bus is broken insulators and loose bolted connections. In this case, they tightened the bolts too much and they snapped the heads off, or snapped the bolt in two, and they left it. You know, all it took was to say, hey, we need new bolts, and taken it out and put new bolts in. But they didn't, they left it that way. So that bus would have failed, and they did not know they had a bolting problem till we did the EMSA testing. Every bus has expansion joints. You have temperature cycling, you have weather conditions, so they expand and contract. Very popular are leaf type expansion joints. They work, harden, and break. This particular one is about 30 years old. The blue curve is what we saw in 2003. We went in, did an inspection. We found all these cracked leaves. They rebrazed this, if I remember correctly. They didn't take it out. They just welded it back together. 2006, we went back. That was the red curve, and it went down. So since the arcing was gone, they knew the maintenance was good. And this whole pattern is low, so there's really nothing wrong with the generator. Only problem was in the broken shunts in the bus. So to summarize, EMSA has the ability to detect and classify a variety of problems, both electrical and mechanical defects. You can then schedule condition-based maintenance and focus only on the system that need maintenance because deterioration is indicated. You can reduce the number of in-service failures. You can greatly reduce your maintenance costs because you'll have an idea of what the problem may be and where to look. And what I like to stress, if there's no indication, you can safely postpone doing any work on that equipment. And several people rely on that. I showed you examples of generators with no problems. They can postpone pulling the rotor for another year or two. Keep it in the 5-year plan, but you're not going to do it next year. Here's a list of conditions found with motors. Dirty stator windings are by far the #1 problem with motors. The end windings and end arms can get loose. Most modern motors are VPI'd, so they're glued in the slots, so they don't become near as loose as the older ones do. Broken rotor bars is very common if you've got a big fan you're starting. We have picked up field grounds on a large synchronous motor. Not setting a motor on a magnetic center, the rotor will thrust back and forth. We can pick that up. Loose foundation, white bearings, outboard insulation on most large motors is insulated. That can fail or short. You can get a seal rub. Again, the sniffer tells you exactly where to look. Now, the sniffer won't tell you whether it's a bearing insulation problem or a seal rub, but it will tell you to look at that bearing. So when you open it up, you can find what the problem is. Weather seal rubs on an exciter of a big synchronous motor, pump motor. Coupling misalignment I talked about earlier. And this can also be in a gearbox for a fan or a pump. Coupling insulation missing, circulating currents in the pumps, the mills, the gearboxes, the fans. Often they do not demagnetize gears in gearboxes. So if you have a rotating magnet, you produce current and this will chew up the gears. We found that in many steel mills. And loose neutral connections. Loose connections on the line side, power factor correction capacitors, abrasion on the stator windings where sand has eaten away the insulation on the windings. Defective motor lead insulation. We found several people that put in leads that don't have enough insulation on them. Wet power cables, I showed you an example of that. Stress cone problems, and you can verify that the maintenance you performed was or was not good. For generators, similar things, slot discharges, which are a constant problem, loose end windings, loose wedging. Now, on this, EMSA will not detect loose wedges. It will detect loose stator bars, the 2-load test, for example. But you have to have loose wedges to have loose bars. Phase rings or circuit rings loose and moving around. Again, the 2-load test is very good with that. Verify the problems were fixed or not fixed. Flux shields, this was on a big brown Bavaria generator. Contamination, alternator or main field slip ring sparking. Defective diodes we talked about. Brushless exciter, we found one down in the Dominican, oh no, it was in Jamaica. A brushless exciter that was ready to explode because it was so bad. power cable problems. Bus conditions, same thing, loosened and cracked and broken insulators, contamination, hardware that's corroded, stray circulating currents outside of the bus enclosures. Some types of isophase bus have a lot of insulation to separate the enclosures. That goes bad with time. Foreign metal objects, we found chain falls on the inside. We found solvent cans on the inside of bus. Potential transformer connections are very common on the PT. High voltage fuses will open up, and transformer problems. So that's it. I hope somebody has some questions, and then I can go back to elucidate on those. So thank you very much.
Thank you, James. Thank you. Actually, I have a few questions. The first one is what distinguish the differences between the EMI inspection and the EMSA?
You mean partial discharge or EMI?
Yeah. The partial,
Okay.
the partial discharge, of course.
Partial discharge analysis, PDA, was developed in Canada, in the 70s, and it was focused on looking for stator problems on large hydro generators. And at that time, Greg Stone worked with Ontario Hydro, and then he formed IRIS. And the PD analysis looks at the higher frequencies. It looks for slot discharges, and it's a very good technology if you want to look at the generator only, okay? And it works quite well for finding partial discharges in stators. So what Greg Stone basically looks like is this part of the frequency spectrum here, 80 megahertz and higher. What we have found is we need to look at all of these frequencies to pick up everything. And like I mentioned, we, especially for motors, this particular one, there's almost nothing above 10 megahertz. We stop at 30 megahertz. So looking at this frequency range with partial discharge analysis for 4 kV equipment doesn't pick up anything till it's almost ready to fail. And they recognize that and admit it. You've got to look at these lower frequencies for 4 kV and 3.3 kV equipment. And for other problems, like what we're doing for exciters, looking at these lower frequencies is very important, and PDA doesn't look at that at all. So it's basically, and the other thing is this is a frequency domain analysis, frequency versus amplitude. Partial discharge analysis is amplitude versus time. So it's a different way of looking at it. The mechanical problems like arcing shaft ground brushes and that sort of thing, PDA can't pick up.
Okay, and then another question. What kind of factories, plants, or substation do you recommend to use the EMI? Is it limited to small scale factories and plants, or it's good for as well as large scale?
We have applied it to small hydro generators in Bolivia, small internal combustion engine generators in Central America, up to nuclear size units. So whether they're gas fired, this particular one, if I remember correctly, is in the Philippines, and it's a geothermal plant. So any size can be used. Like I mentioned, we've been at many petrochemical sites, plastics, refineries, and chemicals, paper mills, all sorts of desalination plants. We've tested a lot of motors at desalination plants over in your part of the world. So just about any size. The examples that I used here on the generator, this is a very small unit that runs off of sawdust up in Northern California, and they don't want to pull the rotor. they get paid to generate, so their makeup costs are extremely high. So they wanted to postpone working on this generator for a few years, and like the curve shows, there's nothing wrong with that generator. So they put it off, I think, 4 years in their 5-year plan. And you know, the cost of doing an EMSA test on that generator versus pulling the rotor when they didn't need to was, again, about 10 to 1. So any size unit we'll use. The largest one we've tested so far have been 1100 megawatt nuclear units, and we've tested probably about 6 of those.
Okay, and another question. Is the EMI good for repair job confirmations, the quality of the repair jobs, as well as the fault detection?
Well, yes, that was the reason for this example here. This is a large motor. We found a bad bearing, they repaired it, and the curve changed dramatically. So yes, that is one thing you can do with this. I've been amazed that with partial discharge analysis, they've never done that. And of course, that can be done with PDA also. EDF in France, I'm sure, has written some papers on that. But yes, with EMSA and with the sniffer, you can tell that you've corrected the problem. You know, you clean this motor up and then that will disappear. So, yes.
Okay, so if anyone have further questions, you can tell us right now, and if not, then we'll finish. Okay. So thank you, James. Thank you a lot. It was very interesting. By the look of the attendance, I see a lot of people that showed up. And thank you, everyone. Thank you, everyone, to arrive. And that's it.
Well, thank you very much, and have a pleasant day.
Pleasant day. Thank you.
James, thank you very much.
All right, very good. Appreciate it.
We will talk later.
Okay. All right. Thank you. Bye.
Bye-bye.
ביי.
ביי ביי. עדי, תודה רבה.
בשמחה.